1.11 video over variation. Okay, I'm going to quickly review the different types of variation. First, we've got direct variation, where y is proportional to x. If you look at this, it looks just like a linear equation, and it is. It's a linear equation where one point is given, and then the other point is assumed to be the origin. Okay, inverse variation is a little bit differently. This is y is inversely proportional to x. Notice that y is equal to k divided by x. This is actually a rational parent function. So this is not a line at all. It's actually a curve, and it's usually decreasing in nature, meaning as x increases, y is going to decrease. Okay, so we could even write this here as x increases, y is going to decrease. And there's lots of examples that you probably went over this with last year. We're going to see a few of them here. With direct variation, y tends to increase, and then as x increases. Okay, so there's an increasing for both, or there could be a decreasing for both as well. You might consider when k is negative, but generally with direct variation, k is not negative, and it's a straight proportional relationship where you could even solve it with a proportional. Now, joint mostly just means that we have more than one variable. However, if you see the word jointly proportional, it is assumed that x varies directly with z, y varies directly with z. How do you think x and y are varying towards each other? Okay, they actually have an inverse relationship towards each other. All right, and we can see that because they're being multiplied to each other. And k is called the constant of proportionality. If I ask you for that, I'm just asking you to find what k is equal to. So number one says, during a thunderstorm you see lightning before you hear the thunder because light travels much faster than sound. The distance between you and the storm varies directly, so I'm going to circle that. That's going to tell me which type of variation to use, as the time interval between lightning and thunder. Alright, so suppose that the thunder from a storm 5,400 feet away takes 5 seconds longer than the lightning to reach you. So they're giving me two numbers. Determine the constant of proportionality and write the equation for the variation. Alright, so let's first write an equation. It says the distance between you and the storm varies directly as the time. So I'm going to let that be distance equals k times x, but in this case x is going to be t for time. So this looks a lot like d equals rt, and we're going to get into that in the next part. So in solving for k, okay, I need to plug in these numbers. Okay, so 5,400 in for d, and then k times 5. And for solving for k, notice that you actually divide. Now this may be confusing, like when do I multiply, when do I divide? Well, if you just follow the original inverse or direct or joined or whatever, you don't have to memorize that because you can just use good algebra skills. Just plug it in where it needs to go and then do what you need to do algebraically to solve. So in this case, I'm going to divide 5,400 by 5, which is going to give me 1,080. Alright, so that is the constant of proportionality, and that's all they're asking me on this first part. Alright, now if they were asking you to write the equation, what we would want to do is go back through with our original equation, d equals, instead of k, we would write 1,080 in t, and that answers the second part, which is write the equation. So both of these are answers, just to the two different parts. Okay, so let's look at part B. It says, what does this constant of proportionality mean or represent? Well, I already saw that k was kind of replacing r in my d equals rt, but what rate is it talking about here, considering that we're talking about distance and then time that you hear thunder and see lightning? Okay, so this right here, this r, or this k, this is not quite the speed of sound, but it's really close to the speed of sound. Now, why would it not be exactly the speed of sound? Well, you've got a couple of things going on. You've got your lightning. Now, the speed of light is pretty quick, but it's not instantaneous. Alright, now in a lot of purposes we consider it to be instantaneous because it's so much quicker than sound. But there's also other reasons, and that has to do with the fact that sound, for thunder especially, may not be a direct wave. There may be interference or echo or things that might cause this to change. But this, if you look up the speed of sound in these units, it's actually pretty close to it. All right, so now let's look at the last part. We're going to use this equation to make a prediction. So remember that our equation was D equals 1080 T. So it says, if the time interval between lightning and thunder is 8 seconds, how far away is the storm? All right, so this 8 seconds, you got to figure out, are they giving you D or are they giving you T? It should be fairly obvious. In this case, it is that they're giving you T. So we're finding the distance. So again, it's not about memorizing whether you have to multiply or divide. Just use good algebra. Plug in T. It's obvious that I have to multiply. And that gives me 8,640. And these are pretty easy calculations, but if you needed to use a calculator, you could. It's a word problem, so you would have a calculator on the test that covers this part. Okay, so now let's look at the second one. This is science application, chemistry. So Boyle's law states that when a sample of gas is compressed at a constant temperature, that's important that we're going to assume temperature to be constant. The pressure of the gas is inversely proportional to the volume of the gas. So I see inversely. The pressure, let's just go ahead and, before we even read part A, let's write down what we know. The pressure is, and then K. Now I'm either going to multiply by volume or divide. It depends on the type of variation. Now remember that inverse variation calls us to do K divided by that independent variable. And so I'm going to do K over the volume. Now where temperature should go in this, you may know if you know this formula, but we're considering the temperature to be insignificant, or not so much insignificant, but constant. So it's not playing in part to this K. So suppose the pressure of the sample of air that occupies 0.106 cubic meters at 25 degrees Celsius. So this is going to stay this way in this entire problem. We don't know how to do anything besides 25 degrees Celsius. And that's 50 kilopascals, or kPa. So find the constant of proportionality and write the equation that expresses the inverse proportionality. So we've got to plug these two numbers, not 25 degrees Celsius. Again, that's an assumed number right now. But we need to plug 50 in for the P, because that's the pressure. And we need to plug 0.106. Now, I don't have to worry about changing units or anything, but once the units are set, you've got to stay with those units for the rest of the problem. All right, now how am I going to find K? If you just think this through algebraically, K is going to be 50 times 0.106, and this might require a calculator, or would. And so that's going to give us 5.3. So that is the first answer. What is the constant of proportionality? And this is going to be particular to this gas at this temperature. It will change if those parameters change. All right, so the last part should be pretty easy. We just take our K and we plug it back into our formula. So the pressure is going to equal to 5.3 divided by the volume for this gas, for this temperature, for these units. If anything changes, this will not necessarily be a formula I could use. All right, so part B is going to ask us to make a prediction. They're saying, well, suppose that the sample expands to a different volume. Find the new pressure. So again, I'm trying to find the pressure. I know the constant of proportionality. I know now the new volume is 0.3, so you just need to do the division here, and that's going to give you your new pressure, which, since we're dealing with decimals, you could go ahead and write a decimal answer. Just make sure you round to 3 decimal places, 17.667, and that's kPa as our units. Make sure you use the same units. If by chance this volume had been in different units, I would have to do that conversion first before I plug it in. Got to keep the same units. Okay, last problem. Newton's law of gravitation. That says that two objects with masses m1 and m2 attract each other with the force F that is jointly proportional to their masses and inversely proportional to the square of the distance r between the objects. Okay, before we move on, well, the rest of the directions say, express Newton's law of gravitation as an equation. Use the traditional notation G for the gravitational constant of proportionality. We're going to go ahead and use K first, and then we'll plug in G. So this is force. Force is our ultimate dependent variable. Okay, force is jointly proportional to. All right, so we're going to have K. Now, jointly proportional implies direct. So they're masses. So we're going to multiply M1 to M2. All right, now then it's inversely proportional to the square of the distance. So I'm going to divide, because that's what you do with inverse. I'm going to divide by r squared. All right, now this is my formula. It does say to go ahead and use G, since they're just going ahead and telling us that that's what K is representing here, gravity. And so F equals G M1 M2 over r squared. And this might look familiar in physics, or something at least like it. Okay, now one last thing that's not typed here, but something that I want to ask you is, I want to ask you, what will happen to the force if I double, and let's just say I double one of the object's masses. So if I double M1, what will happen to the force? Well, if you think about it, this may seem obvious, but I'm going to go ahead and plug in twice M1, more to kind of lead to the second thing that I'm going to show you. So if I multiply M1 times 2, that's ultimately multiplying force times 2. So that will double the force, which you might have predicted, and that would have been a good prediction. Now, if you double both objects' mass, that's like a doubling of doubling. That would be a quadrupling. Okay, another strange thing that would happen is, let's say we don't want to double the mass, we want to double the rate. Okay? Or I'm sorry, not the rate. R is standing for the distance between the objects. So we're doubling this distance. Now what do you think is going to happen to the force? I'm going to go ahead and tell you that's not doubling. Now, if you're not sure, let's just plug it in. This is what you could always do if you're not sure, or if there's many things happening. So instead of r, I'm going to write 2r. Now remember that you're squaring it. You're squaring this distance. So I have to double it and then square it. That's actually times 4, which is not a doubling anymore. This is a quadrupling. And so you're going to get to practice this a little bit on your assignment. But you just got to think logically. This is all stuff that you learned in geometry back with perimeter and area, like if you double the dimensions, what happens to the area? Okay, but it's applied in these situations as well, so you just have to be aware of that. Okay, bring your questions to class.